Hello to the welcome to the ninth lecture for the mathematics class 11 chapter 4 complex numbers and quadratic equations. So we are towards the end of the chapter. So we learned how we can have different algebraic operations working on complex numbers. We saw how the imaginary unit I is useful while finding the square root of negative real numbers, and we have also seen how we can find magnitude and conjugate, and how you can utilize those to simplify expressions or questions that are given with respect to the complex numbers. So these are the some things we have done till now. So in the last class, we had started with eigenplane and polar representation. Okay, so we had started with this aspect of complex numbers where we can geometrically represent a complex number, okay, in terms of x-axis and y-axis. So just a small revision. So you have x-axis and you have y-axis. This is the real axis and this is the imaginary axis. Okay, and you have positive side and negative x-axis here. Then you have positive y-axis and negative y-axis. Okay, so suppose if you are given the complex number 2 plus 3i, so it can be represented as point P, which has in the form of pxy. So the x is actually the real part and y is the real coefficient of the imaginary part. So then P becomes 2, 3. Okay, so if you want to represent it on the eigenplane, you take 2 units of x and 3 units of y. Okay, so you have 2, 3. So this is your P. So this would become P 2, 3. Okay, and then you also can find the angle. Okay, that is also called the argument of complex number. So that is actually the theta. So that is the angle between the real axis and measured towards the complex number. Okay, so this is your theta, and theta can also be given as tan inverse of y by x. Okay, so these are some things we saw. This is the argument of z, and to find the magnitude of z, okay, so the magnitude of the complex number z, we can find the modulus of z, and that would be over here, since we are denoting z in the form of now x plus iy. Okay, so actually that would be similar to how we had seen how we can find the modulus of a squared plus b squared and whole under root. Okay, so similarly this would be under root x squared plus y squared. So this is the magnitude of dz and this is the argument of dz. Okay, so the theta. Now there is another way of representing complex numbers. Okay, so now we can also represent complex number in terms of trigonometric functions. Okay, so over here you can see you have this form. Okay, so this is called the polar form. So this is the polar representation. So if you write z is equals to r cos theta, if you open up the bracket over here, okay, so r cos theta plus I r sin theta. Okay, this represents the general form x plus I y. Okay, so this is in the same form. So we can write r cos theta is actually the real part of the complex number, and r sin theta denotes the real coefficient of the imaginary part. Okay, so that is the y. Now what is r over here? So r is nothing but the magnitude of z. So that is actually the modulus of the complex number. Okay, so again you find x squared plus y squared. Okay, so this is your r, and theta again theta we know we can find using the argument, the formula that we have for finding out the argument of the complex number. So tan upon y by x. Okay, so this is how you can find the individual, individual parts of this polar form of representing a complex number. Okay, so this is what we have seen. So actually, when you plot it in the Argand plane, suppose we, okay, so this is your p x comma y. This is your complex number. This is x and this is y. So actually, this distance OP is your r, and the angle measured from the real axis in the direction, okay, in the anti-clockwise direction in the towards the complex number is theta. Okay, now actually if your complex number is in this is your first quadrant, this is your second quadrant, third quadrant, and fourth quadrant. Okay, so you can see that there are four quadrants. The Argand plane or any Cartesian xy plane also can be divided into four quadrants. Now over here you can see, so if your complex numbers fall in the fourth quadrant or say third quadrant, the angle measured is in like the opposite direction. Okay, so it does not go the full, it won't be measured in the in the anti-clockwise direction anymore. Okay, it will be measured in the clockwise direction when it is in third or fourth quadrant. Okay, so this is your theta 2, theta 1, and this would be your theta 3. Okay, so the way we measure the angle or the argument of z when we have the points in different quadrants is different. So now if let's solve a few examples. Okay, so where we will see how the argument and the magnitude of z can be represented. So let's keep this x, y over here. Okay, so this is your x, y, positive, positive, negative, and negative. Okay, so let's take a few examples. Okay, so let's take z is equals to -1 minus I root 3. Okay, so if we have to, write z in the polar form. Okay, so polar form, as we have seen before, polar form is given in terms of z is equals to r cos theta plus I r sin theta. Okay, so we have to find r over here. So first we will find r. R is nothing but the modulus of z. Okay, and that is going to be under square root minus I squared plus minus root 3 squared. So that is going to give you 1 plus 3 root 4 is equals to 2. Okay, so your r is 2. So now we will find what is cos theta and what is the value of sin theta, because we want to find the argument. Okay, theta also we need to find. So now if you equate it, okay, if you equate the polar form with the general form x plus iy of the complex number z, you can write that r is equals to r cos theta, okay, is equals to x, and r sin theta is equals to y. So over here your x is minus y and your y is minus 3. Okay, so you can put your value of r over here, cos theta is equals to -1. And then your 2 sin theta is equal to -3, root 3. Okay, then you will get cos theta is equals to minus 1 by 2 sin theta is equals to minus root 3 by 2. Now, as per your, mm, if you like for when you have trigonometric functions, okay, so even when we have this plane, there are a few rules that are followed. So all your trigonometric functions, all functions are positive in the first quadrant. Okay, so this is your first quadrant. So all the functions that you have is cos theta, sin theta, and tan theta, and then you have sec theta, cosec theta, and cot. So these are your trigonometric functions. Okay, so these are your trigonometric functions. So when we say all are positive in the first quadrant, all are positive. In your second quadrant, only you have sine as positive, and because sine is positive, your cosec will be positive. Okay, cosec theta will be positive. In third quadrant, sorry, this is your second quadrant, and this is third, and this is fourth, this is first over here, and this is 0 for origin. In third quadrant, you have positive tan theta and positive cot theta. And in the last quadrant, fourth quadrant, you have positive cos theta and you have positive sec theta. Okay, so you have to remember this when you are doing, when you are asked to get the polar form of a complex number, it becomes easy. Now over here, you can see that both cos theta and sin theta are actually negative. Okay, so as per that, as per these rules that we have just established, that in the third quadrant, all the functions except for tan theta and cot theta are positive. So your point actually will come in the, your complex number actually lies in the third quadrant. Okay, so since cos theta and sin theta are negative, Z lies in third quadrant. Okay, so now we know this. Now, as we were saying that in the first two quadrants, okay, you measure the angle from the real axis, okay, towards your negative real axis in the anti-clockwise direction, and for the fourth and the third quadrants, you actually measure it in the opposite direction. Okay, now since it is in the third quadrant, we actually can get theta. Okay, now over here, we know that uh, cos of uh, cos of 60 is actually half, and sine of 60 is root 3 by 2. So from here we can see that theta is equals to minus 60. Now you write it in the radian form, so that is so this will be minus pi by 3. Okay, now since we know that it lies, we do not want to denote it in this form, okay, in minus pi by 3 form. So what we do is we write theta is equals to minus pi, so that is 180 minus the theta that we got over here, okay, and that would be minus 2 pi by 3. Okay, so this is actually the argument of Z. Okay, you can represent it in this form, or like if you have cos theta, now you have already found the cos theta value, so you can write it in this form also. So you what in polar form, in polar form, you can write this as 2 multiplied by minus half. Okay, and you will actually end up getting the same form as this. Okay, you can see that it actually comes up to that. So we actually get the theta first. Sometimes you might be given the theta and you might be given the magnitude. So then you can write it in this form first. Okay, like you first find the cos of the theta and the sine of the theta, and then you substitute for the value of the magnitude that is given, and then also so polar form, if you just substitute the values that you have got, and then you have 2 into minus root 3 by 2i. Okay, so what you get is minus 1 minus root 3i. Okay, so it's the same way. If you just, write it in the, if you substitute in polar form. Okay, so this is how you find the argument as well as the magnitude uh, of a complex number. Okay, now let's take another example. Okay, so suppose you are given the expression 1 plus I, find modulus and argument of z. So let's first simplify z. Now over here you can see this is in the form of z1 by z2. Now if we remember, you can use the relation that where z inverse is equals to a by uh, z inverse is a squared plus b squared plus I minus b by a squared plus b squared, or your z inverse is equals to conjugate of z upon whole square of the modulus of z. Okay, so you can directly substitute for this over here. So you have 1 multiplied by the conjugate of 1 plus I, so 1 minus I, and square of modulus. So modulus would be actually uh, you will have to square the coefficients over here. So that is actually 1 square plus I square. So you get 1 minus I upon 2. This will be actually minus, sorry. I'll just change this out. Sorry. Or you can actually, I think there's something. Actually, if you find the modulus of 1 plus I, you will get this as 1 plus 1. Okay, so yeah, we don't consider the I over here. So that was my mistake. So you will get root 2 as the modulus of the denominator. Okay, so the complex number in the denominator. So now you can write this as the conjugate of 1 plus I, so that is 1 minus I upon uh, root 2 squared. Okay, so you have 1 minus I upon 2. So you will get this as 1 upon 2 minus I upon 2. Okay, so now we have to find the modulus of this. So now the mod of z will be root of 1 by 2 squared plus minus 1 by 2 squared. Okay, then you will get this as 1 by 4 plus 1 by 4, that is root 2 by 4, and you get 1 by root 2. Okay, so this is your mod of z. Now we will find the argument of z. Okay, so argument of z. So if you write this in the suppose we have mod of z is equals to 1 by root 2. Okay, and that will also be equal to r. So we also know that z can be written in the form of r cos theta plus ir sin theta. Okay, and then you will get this as z is equals to 1 by root 2 cos theta plus 1 by root 2 sin theta. Okay, so you will get that, you can get it in this form. So we have already seen that we had actually simplified for z, and z we got it in this form. Okay, so you can write that over here. So z is equals to 1 by 2 um, minus 1 by 2, or plus, it will be easy for us to generalize it. So 1 by root 2 cos theta plus I 1 by root 2 sin theta. So therefore, 1 by root 2 cos theta is equals to half. Okay, so you equate for the real parts and for the imaginary parts. And 1 by root 2 sin theta is equals to minus 1 by 2. Therefore, cos theta is equals to 1 by root 2 and sin theta is equals to minus 1 by root 2. So we know that for 45-degree angle, we get cos theta as 1 by root 2 and sin theta also as 1 by root 2. Now you have a negative sin theta and a positive cos theta. Okay, so since cos is positive and sin theta is negative, so z lies in, if you remember the four quadrants that we had mentioned, and we had mentioned the different properties, it will lie in the fourth quadrant. Okay, because over here you have positive cos theta and positive sec theta. Okay, so this is the only quadrant where you have negative sin theta but positive cos theta. So lies in the fourth quadrant. Okay, and so therefore theta is equals to minus 45 degree, and that will be minus pi by 4. So minus pi by 4, it will actually come over here. Okay, so if you get like 45-degree angle, so this is where you get your z. This is where your z will lie geometrically. Okay, because we are getting it in the anti-clockwise direction, and you have a negative sign for it. So your argument is minus pi by 4. Okay, and the magnitude of the modulus of the z is found as 1 by root 2. That is the r. So this is an example of it. Now let's see another example for your this similar modulus and argument and in the arc and plane scenario. So the question is that z is equals to 1 plus I upon 1 minus I. Okay, so you have to find the argument of z. Okay, so first simplify this. You have 1 plus I upon 1 minus I. Again, we can write the denominator form in the denominator in the form of the z inverse. So you will have 1 plus I multiplied by conjugate of the denominator. So that is 1 plus I. And you get the square of the modulus of this. So this would be actually 1 squared plus minus 1 squared. So if you get this, so you have 1 plus 2I plus I squared upon 2. Okay, so minus 1 becomes 1. And so 1 plus 1, 2. And that you will get, if you, this becomes like, since I squared is equals to minus 1, you get 2 by 2I. So this is I. Okay. Now over here you can see that there is no real part. So this is actually a purely imaginary number and you can write it as 0 plus I. Okay, so now we have 0 plus I. So we want to find what is the argument of this number. So before that, we will try to find the modulus of the Z. So that is root of 0 plus 1 squared. So you get this as 1. Okay, so your mod of Z is equals to 1. Now in the polar form, you have r cos theta. Z is equals to r cos theta plus I r sine theta. Okay. And we also know that Z is equals to 0 plus I. So if you equate, you have R. So R is actually equals to the modulus of Z. R cos theta is equals to 0 and R sine theta is equals to 1. Okay. So your cos theta becomes 0 and sine theta is equals to 1. Now we know that only when theta is equals to 90 degrees, cos theta is 0 and sine theta is 1. So your theta or argument of Z is actually pi. Okay, so this was an easier example, but the thing is that you will have to first solve any of the expressions that are given and then you can find. So now let's see some varied examples where we will try to use, different kinds of operations, whether a combination of operations or, probably mostly we can use the modulus and the different kind of multiplicative multiplication operation or any of the properties of the multiplication or quotient or identity. Okay, so let's take a simple example first. Question is equals to Z is equals to 3 minus I. Okay, so find Z squared. Okay, so now to find Z squared would be equal to Z comma Z. So you can just write it as 2 minus 3i, 2 minus 3i, or you can just expand your using the identity. Okay, so over here you will get this as 4. So minus 2ab. So 2 into 2, 4, 4 into 3, 12. So this becomes 12i, and you have 9i squared. And over here, since I squared is equals to minus 1, this becomes minus 9. So you get this as minus 5 minus 12i. Okay, so this was an easy example. This is how you can find it. Now we will take another example. Say you are given 1 minus 3i upon 2 plus I minus I 5i. Okay, so you have to write this right in the a plus ib form. Okay, so you have to simplify it and get it to a complex number form. So let's take this plus I minus 3 plus I upon 5i. Okay, so we will first solve each of these individually. Okay, so obviously you can do it like how we add these, multiply and then divide for the normal when we are having fractions into play. But for complex numbers, to simplify our process, okay, so we will first solve each of these terms individually and then we will combine. So again, this is in the quotient form, division form. So you can put the denominator in the terms of multiplicative inverse. Okay, so this becomes 1 minus 3i. So you can write the 2 plus I in the form of the multiplicative inverse. So just the formula though that we will use is this. Okay, so now we put this as 2 minus I, that is the conjugate of the denominator, and you will have 2 squared plus 1 squared. Okay, since you have only I. Then you will have minus 3 plus I. And similarly with 5i, you can write the conjugate of it as 5i. And you obviously, when you want to find the modulus of your denominator, so you will get that as 5 square. Okay. So then what you will get is 2 minus 6i minus I plus 3i squared divided by 5 over here. Okay, because 4 plus 1, 5, and then minus over here, you will get this as minus 15i minus 5i squared. Okay, over here, and this you will be getting 25. So now simplify this again. So this since I squared is equals to minus 1, this becomes minus 3. So minus 3 and 2, so you have minus 1. And this becomes minus 7 upon 5, 7i. Okay, and then you have plus 15i over here. Okay, you have plus 15i. And you can, we can actually keep the negative sign for, but we can change it. So we have plus 15i, and this since I squared is equals to minus 1, this becomes plus 5, and then it becomes minus 5 and upon 25. So to get the common denominator, we can multiply the first term by 5. So you get 25 in the denominator, and this is minus 5 minus 35i, and this remains 15i minus 5, and this will be minus 10, and you will have minus 20i upon 25. If you take 5 out, this is what you get, minus 2 minus 4i upon, sorry, you will actually get it cancelled. So the 5 does not come here. Yeah, so if you take out 5, so you are getting 2 minus 4i upon 5. Okay, so your answer is, and so you can just write minus 2 by 5 minus 4 by 5i. Okay, so this is your answer. So you can see that we can simplify any expression in the form of the AI or A plus IB. Okay. Now let's take another example. Okay, so suppose you are given that Z1 is equals to 2 plus 8i, and you have Z2 is equals to 1 minus I. So we have to find modulus of Z1 by Z2. Okay, so if you remember, we had seen that, we had also proven that there is a relation that we can use, that the modulus of Z1 by Z2, okay, is equals to the division of individually, finding the modulus of the individual complex number. So that is mod of Z1 divided by mod of Z2. Okay, so let us first find modulus of Z1. So that is 2 plus 8i, and that would be square of, you have the square of 2 square plus 8 square, that is 4 plus 64 equals to root of 68. Okay, so you can get that Z2 is equals to, you have 1 minus I, that is 1 plus 1 squared. Okay, this is minus 1 squared, and that is 1 plus 1 equals to 2. Okay, so now we have this. Okay, so we can get it as, okay, so you have Now, if you want to find root of z1 upon root of z2 is equals to root of 68 by root of 2. Okay, now if we know that, if you multiply 34 by 2, you will get 68. So since it's in root, the answer actually comes down to root of 34. Okay, so this is your final answer. You can do it in this form also, or you can first find your z1 and z2. Okay, so alternate alternatively is alternate. You can first find the solution for z1 and z2 and then get the modulus of the solution that you get for the z1 by z2. Okay, so you can do that too alternatively. Let's see another example now. Okay, so if you have z squared minus 1 is equals to z squared under modulus plus 1. Okay, if show that z lies on an imaginary axis. Okay. So for z to lie on the imaginary axis, okay, so your x should be 0 if you have z is equals to x plus iy. Okay, to fulfill this condition. Okay, so let's see whether we can get x is equals to 0. So we will first take let z is equals to x plus iy. Okay, so let us first find what would be the value of z squared. So that is x plus iy squared. You can expand it with the identity itself. This 2xyi plus I squared y squared. Okay, so you can simplify to x squared plus 2xyi. This will be minus y squared. Okay, so this is what we get since I squared is equal to minus 1. Now we can then write z squared minus 1 is equals to x squared plus 2xyi minus y squared minus 1. Okay, and if you bring all the x terms and the y term to one side, plus I to xy. So you can have, all the real terms on one side and the imaginary term on the other side. Okay, now we have to find the modulus of this. So the mod of z squared minus 1 will actually become under root x squared, sorry, this will be minus x squared minus y squared minus 1 squared plus square of this 2. So you have 4x squared y squared. Okay, so this is what we get. Now you can simplify for the first bracket that we have. So you can write it in terms of x squared minus y squared minus 1. So multiply each of the terms over here. Okay, and this will actually turn out to be, so this actually become x raised to 4 minus x squared y squared minus y squared x squared plus y4 minus y squared minus x squared plus y squared plus 1. and then you have plus 4x squared y squared. Okay, so that will then become, you will see over here that you can actually cancel out the squared ones. Okay, so you have plus y squared minus y squared, you have minus, actually this would be, I think this sign will change. Yeah, minus, this sign change. Let me just check once. X squared, x squared, y squared. There will be, I have missed another one. So there will be one x squared value over here. So you can actually cancel out your x squared and y squared terms. So what you remain with is actually x raised to 4 minus 2x squared y squared plus y raised to 4, and you have plus 4x squared y squared. So this will be equal to, you can write, this actually then becomes x raised to 4 plus y squared plus 2x squared y squared. Now this is actually in the form of x squared plus y squared the whole square. You can write this x squared plus y squared the whole square, and you can take out the root sign, and what you get is x squared plus y squared. Okay, so this is what you get. Okay, now we also have to find the right hand side. Okay, so over here we found the value of the left hand side of this equation. Now we will find the right hand side of it. So root of modulus was, interchange it. Yeah. So this would be square of the modulus of z plus 1. Okay, so this is what we found. We have to find. Now we have already seen your z square. Okay, your z square is actually is equals to this. Okay. So your z square, the modulus of then z, you can find. So the modulus of z is, you can write this as x squared plus y squared. Okay, and the squared of this plus 1. So then this becomes x squared plus y squared plus 1. Okay, now since we already know, we are given that z square minus 1 is equals to z square plus 1. Okay, so it would be inside this. So yeah, so this is already given to us. So hence we can then equate both the left hand side and the right hand side that we have got after solving. So you get this as root of x square minus y squared minus 1 the whole square plus 4x squared y squared, okay, is equals to x squared plus y squared plus 1. So now you can equate this in terms of, now if you square both the sides, you get both sides, you get x squared minus y squared minus 1 here plus 4x squared y squared is equals to squared plus y squared plus 1 the whole square. Okay, now you can try to get it in the form as x squared, okay, minus y squared plus 1 the whole square plus 4x squared y squared is equals to x squared plus y squared plus 1 the whole square. Now you can see over here that this and this, okay, so this can be in the form of a squared minus, or you can actually a minus b the whole square, and this can be thought of to be in the form of a plus b the whole square. So over here a is equals to x squared, and b, your b is equals to y squared plus 1. Okay, so if you keep it in that, and then if you want to see what do you get, okay, you try to get these two in the same side. Okay, so if you have okay, and then in continuation you can get your x squared minus y squared plus 1 the whole square, and get minus x squared plus y squared plus 1 the whole square is equals to, or you can write for x squared y squared is equals to 0. Okay, so now since we are writing this in the form of a minus b squared and this as a plus b squared, now if you actually calculate in the general identity form, okay, so what you will get is this would be equal to a squared minus 2ab plus b squared. Okay, and now if you get this as, you keep the minus sign, so you already multiply the minus sign with the expansion of a plus b the whole square. So you have minus 2ab and minus b squared. Okay, so over here you can cancel these out. What you are left with is minus 4ab. Okay, so if you have to write this in terms of this, so this actually becomes, what is minus 4? Your a is equals to x squared, b is equals to y squared plus 1. So minus 4 into x squared multiplied by y squared plus 1. Okay, so therefore minus 4x squared y squared plus 1 plus 4x squared y squared is equals to 0, and this becomes 4x squared y squared plus, not plus, this will be minus. Sorry. Yeah, yeah. So this would be minus 4x squared plus 4x squared y squared is equals to 0. Okay, so over here this and this will get cancelled. You have minus 4x squared is equals to 0. So therefore x is equals to 0. Now you can see that to actually prove this, show that z lies on an imaginary axis, we had to find that x is equals to 0. So you can write this as hence proved. Okay, so x will be 0, and therefore z lies on the imaginary axis, that is y axis. Okay, so this is how you can find this out. So let's quickly go through another kind of an example. So suppose you are given as z is equals to x minus iy 3 plus 5i and is a conjugate of minus 6 minus 24i. Okay, so if you have this, so find the real numbers x and y. Okay, so if you have an example like this, so let's first solve for z. So x is equal to minus y 3 plus 5i. So this is 3x Okay, and then you have 3yi, you have plus 5xi, and you have minus 5yi squared. So 3x, and this becomes, since I squared is equals to minus 1, this becomes plus 5y. So let's get, since the I goes away, we get the real parts on one side. Over here, let's take I outside, you get 5x minus 3y. Okay, so z is in this form. Now we are given that we know that z is also the conjugate of minus 6 minus 24i. Okay, so you can write this as minus 6 plus 24i. So now if you equate the real parts and the imaginary parts, you will find that 3x plus 5y is minus 6, and 5x minus 3y is equals to 24. Okay, so now let's solve for it. So suppose you have 3x is equals to minus 6 minus 5y, and then x is equals to minus 6y. So I can just directly write this as 2. So this will be minus 2 minus 5 by 3y. Okay, so substitute for your x over here. Okay, so you will get this as 5 into minus 2 minus 5 by 3y minus 3y is equals to 24. We get minus 10 minus 25y. Okay, you take it over here. This is 9y is equals to 3 into 24 will become 3, 12, 6, 72. Okay, so you have minus 34y is equals to 82. Okay, so we get this as y is equals to minus 3. Okay, so now since we got y over here, if you multiply or you substitute it over here, so x is equals to minus 2 minus 5 by 3 multiplied by minus 3, so you get minus 1 here, so minus 1, and so you have minus 1 plus 5 multiplied by minus 5 over here, you get minus 2 plus 5, so x is then actually 3. So the answer that we get is that x is equals to 3 and y is equals to minus 2. Okay, so this is the answer that we get. So we have seen a number of examples, where we have used different kind of operations. We have simplified. We also used the conjugate over here. Okay, so you can find out. It's easy to solve for different kind of problems that are given on complex numbers if the basics are very well, studied and very well understood. And you can use the different kind of properties that we have learned in this complex numbers to answer such questions. So a few of the examples are similar to a few of the examples that have been solved. Actually does include a combination of different operations that can be done on the complex numbers. So thank you for attending these classes, and hopefully this has helped you. All the best.